Welcome, Mark. Thank you. You are the inspiration of this. I still can't exactly place when when I first shared this with you, what, 32 or 33 years ago. I remember at the time Xanadu was kind of in its, Autodesk is pulling out. What are we going to do now? days.
Yeah, yeah. So that would have been around 91.
Oh, okay. Yep. So yeah, I think one of the reasons why I shared was like, I'd like to try to do something with this. Is Autodesk going to stop me? And you said nope.
Yeah, it's that's correct. Autodesk. Well, the Xanadu, all the Xanadu stuff was still proprietary, um, and Autodesk did block us from freeing up the one thing that was not covered under the TED proprietary arrangement,
Oh,
which was trustee scheme. Um, but I think I made the right call that in fact, Autodesk would not think to block a separate release of the club system, especially implemented with a separate mechanism.
yeah. But
They,
anyhow,
yeah,
you were absolutely encouraging me then, and this is in some ways it's never quite left my mind. So in some ways, this is a tribute to that. So thank you for being here today.
you're welcome. Thank you for keeping at it.
Well, I'm not the only one who's been working on some of this stuff for a while, but yes, we just sometimes it just takes time.
Yeah.
So I wanted to welcome everybody to the Blockchain Commons Gordian meeting, where each month we talk a different aspect of open, interoperable, secure, and compassionate digital infrastructure. Today's topic is on Gordian Clubs. For those of you who are not familiar with Blockchain Commons, we're a community interested in self-sovereign control of digital assets and identity. We bring together stakeholders to collaboratively develop interoperable infrastructure. We design decentralized solutions where everyone wins, and we are a neutral, not-for-profit to enable people to control their digital destiny. I have to give a great appreciation to my sponsors over the last couple of years who have enabled this research to happen. In particular, lately, the Human Rights Foundation and the Zcash community grants have contributed to sponsor some of our work. If you're interested in sponsoring us, please let us know so that we can keep these activities moving forward. So at our last meeting, we had a demonstration of Frost signing on the command line, in particular using Bitcoin Development Kit and the ZF Frost tools. If you're interested in seeing that demonstration or trying out our code, it's available on our meetings page. Today's topics is going to be about Project Xanadu, which was, if you're not familiar with it, was way before its time, and then we're going to talk about some ideas from that, in particular around Gordian Clubs. We're going to give you an introduction, a demo, and then I'm hoping to talk a little bit more about the longer term opportunities. So first off, Project Xanadu, obviously inspired by the Samuel Taylor Coleridge poem. The visionary was Ted Nelson, and I believe he's credited for coining the term hypertext. Uh,
Yes.
the goal was a digital repository scheme for worldwide electronic publishing. And you have to recognize that, he first started talking about this in the 60s and, did a major influential book in the 70s. And then Autodesk basically picked it up in the 80s and hired a number of people, including Mark, who is here today, to basically make it happen. And I believe for not quite a decade, they had you working on different aspects of it. Um, I became involved in the early 1990s, kind of in its, trying to get their first public version out. And that was where a lot of this discussion started. So I do have to explain a little bit about Project Xanadu versus the World Wide Web. It definitely was developed well before the internet, and in some ways it had some superior qualities. For instance, it had the idea of two-way links. It had some very interesting ideas about uniquely identifying users and documents and dynamically changing storage. And it had some early thoughts on micropayments. And in fact, that's how I got involved. I went to a conference and basically, said, "Hey, Ted, how can you be saying that a byte is worth a byte is worth a byte?" And, somebody kind of pulled me aside afterward and said, "Who are you? Why are you asking these questions?" And
Was
that's,
that was that Phil Salen?
yes, it was. And he was great. Miss him very much. Um, but in particular, the Xanadu Club system fascinated me. One of the aspects of it was public by default. The root of the whole system, you could kind of think of it in their terminology, would be kind of the root of the World Wide Web was public. Openness was default, and then privacy was partitioning within that. They had this concept of a person as being a club of one. So there really wasn't a distinction between people and groups in the same way that other kinds of systems did. But probably the most important power was that clubs could be members of clubs. So a club as a group could hold rights and be members of other clubs. And this allowed for a lot of interesting recursive uh, opportunities uh, to grant different kinds of access and how groups would function internally. And then when you combine that with a number of not locksmith options, uh, clubs could grant access through a variety of different kinds of mechanisms. And I took all of these to heart. And I'd also, RSA was actually fairly new at that point. I became fascinated by it. And I thought, we could actually do this with RSA. Um, so I want to say a little bit more about why it's revolutionary. So I really like that it had these sort of natural hierarchies without a central administration. And these nested permission structures allowed for flexible governance. Um, and it, through the access control mechanisms, I today we would probably say, oh, those aren't smart contracts, but they really were in a sense. And there was a number of things that the Xanadu team and Phil Salen over at Agorix did that were early smart contracts work. Um, and ultimately, it clicked because it modeled how human trust hierarchies actually work. And I think that was the thing that particularly grabbed me. Here is a diagram from one of the documents back there. Basically, we have Bob, who is a group, can self-edit his club and he can self-read his club, but then he has privileges to be able to edit this poem, the Coleridge poem. But he also has the ability to edit a blind copy group who can read the poem but don't have the ability to edit it. And various parties, Chuck and Alice, have the ability to also participate in this BCC club and thus be able to read Bob's edition. And that's that's from those old documents. And and here is the key quote from the old documents that explains a little bit more about the meta issues that who can read what. And if you're, trying to do this all in one particular type of thing, it could become infinite and big and lots of regression. But the internal loops and self-modification things made it to much more comprehensible.
Yeah.
Um,
Could you back up to the club side? I just want to point out
sure.
one thing here, which is, yeah, when a club is created, it's self-read and self-edit. which means you don't it sort of ties off the meta levels. So you don't start off with an infinite hierarchy of meta levels, but you grow meta levels on demand. I think that was one of the most important things about the club system. So, for example, when the BCC club was created, it may have been created at that moment, disconnected from everything, but created by Bob, um, who had ability to well, and it could have been self-read and self-edit, but then Bob turns it into something that only he can read and edit. And you can so for anything that's just a self-read and self-edit, sort of tying off the meta levels, when you find you need those distinctions, you can grow upward as well as by inclusion of other groups growing downward.
Yeah, and that's exactly the thing that inspired me, and I wanted to recreate for coming on 34 years, because this was actually happened 2 years before I thought. Uh, um, uh, but there is one problem with Xanadu clubs, given sort of today's thoughts on decentralization, is that it's a mother may I. You're still going back to a centralized computer who is looking at this, and as has been discussed in the years since, it really still is sort of an access control list. Um, what I really wanted to do, and what the inspiration that I shared with Mark back in 92 was, oh, I can prove I belong, and that is what will give me access. And uh, but again, we're talking 1991, 1992, but RSA was too slow. RSA was export restricted, so you had lots of problems if you wanted to sell outside the United States. And probably the most important was that, good code didn't exist. I mean, I basically in 93, 94 did RSA Ref, which was really the first implementation of RSA that was kind of publicly accessible. Um, and I wouldn't recommend anybody use RSA Ref anymore. So, but it kicked. It was used by Netscape, by PGP, by DigiCash. All the early cryptography people did that. But until RSA Ref was available, good code wasn't. Later, I wanted to do this in 2001 and discovered that, a lot of the things that in order to make it work, the patents were either too restrictive or just absolutely, too expensive. The timestamp for what, we would today call hash chains and hash trees patent, they wanted 5% of global revenues, and they were just sticking on that. So, and I don't think they ever did anything with it, but that was their story. So this is, for instance, one of the reasons why Bitcoin couldn't have happened until, 2008, 2009, after the hash tree patents expired. Um, Later, I wanted to do this in 2014, but the problem was that the tool I wanted to use, which was Schnorr, Schnorr aggregation was not safe, and in a naive sense, it worked, but it was able to be attacked. And this is what led to MuSig 2 and MuSig DN and Frost and other different types of techniques. But now we're in 2025. The technology is finally caught up to the vision. With Gordian Clubs, we use Schnorr signatures, Frost, our own technology, Gordian envelopes, and ZIDs. And the result is a pure mathematical object that encodes its permissions in their structure. So I need to explain a little bit more about this. The key here is recursive cryptographic capabilities, where the mathematics delegates. This can happen anywhere. Like the original Xanadu system, clubs grant capabilities to other clubs. The difference is there's no administrative intermediary. The chains are pure cryptography. Um, the recursive permission structure allows Club A to grant read access, to delegate subsets of it, all math enforced by mathematics, not code. And thus, I feel like it really fits into the original Xanadu realization. It allows for, hypertext objects to be shared with cryptographic enforcement, and you are what you can prove you can access. So thus, rather than being a simple document, a club is an autonomous data object. Um, with a Gordian club,
Chris,
you go, yeah.
Chris, does that include a way to audit to know
We'll talk a
who?
little bit about that. So, with autonomy comes some limitations. So definitely in the purest form, no, because it's completely autonomous and you can use these clubs completely offline. You could have received this on a USB key and have no active connection, or the connection is extremely latent. That being said, there are a variety of constructions within autonomy that can allow you to do some of this type of stuff. And then obviously when you're online, which you're going to need for certain kinds of operations, you can have constructions where you can't operate without an authority. But we'll talk a little bit more about that later. So in the autonomous case, you receive an edition, and that the contents of this edition is encrypted and verifiable with a signature and a provenance mark. But how you got that edition is completely transport agnostic. Obviously the internet, it could have been peer-to-peer, could have been through Tor, maybe through an NFC card or Blockstream satellite, or as I said before, SneakerNet. Um, so you have cryptographic proofs, and you use those to obtain your read privileges on the edition content. This decrypted edition may reveal that, in fact, there are other editions from the same or other clubs inside it, which you may or may not have access to. So you have as much access as you need, given the authority that has been granted to you by your keys. Um, if you are a member of the right club, you now have the ability to update the edition by authoring a new edition that can be accepted as authoritative due to your cryptographic proofs. So thus, there is no server, there is no database, there is no requirement to phone home. Um, so in order to do this, we have to do access control. And this is what I call cryptographic OCAPs. It is different than the classic OCAPs that Mark and others here have been working on for years. But it is also very similar. We're using mathematics to enforce capabilities and delegation. So,
I just
sure.
want to interrupt for a moment. It says Xanadu OCAPs with cryptographic OCAPs. What you're doing right now is cryptographic OCAPs, but that was the move the move of a club system to an OCAP basis is your invention, not ours.
Correct.
The Xanadu club system was an ACL system. It was not an OCAP system.
Correct. Okay, I see. Oh, I get your distinction there. So, but I think that my point is that you were replacing the traditional system, which, as you know, in the years since we've gone, oh, that actually is still just an ACL, and the OCAP community has, continued to work for these last 3 decades to really, puzzle out a lot of the issues and opportunities and the security for OCAPs. And I just want to be clear, we can't do everything that the traditional OCAP community does. There are limitations on what we can do. That being said, it is very much inspired by what they've been implementing in the last 30 years. And if you're not familiar with it, I definitely encourage you to study how object capabilities work. So how do we do this with cryptographic OCAPs? What we start at the bottom level is with permits. So these are cryptographic capabilities for read access that allow you to decrypt things. And we've made the decision, at least for this version, to focus on Schnorr signatures. And the reason why is that there are some very interesting opportunities for composability in what I call smart signature protocols. In particular, there is a concept called adapter signatures. Note that is OR if you're searching for it. Scriptless scripts will also give you a lot of archive and other cryptography documents that show some of the things going on there. But basically, they allow you to leverage more signatures to give conditional authorization. And that is what really is the heart of an object capability. We've added to that our work on Frost to allow for group decision capabilities. And so this is, fundamentally what we're going to, show you what we're trying to do at this point. For the existing OCAP community, it is the same principles, except for the fact that it's cryptographic enforcement, that these are mathematical objects, and I believe that there is no confused deputy problem because the math doesn't lie. But clearly, it is different than classic OCAPs, and there may be, specific things that we would, love that community to look at and contribute back.
Uh,
Um,
just,
Go ahead.
I'm confused about the phrase "math doesn't lie." I did not spot a confused deputy problem in your design, so it might very well not have one. But what is "math doesn't lie"? How does that relate to that?
Sure, and maybe that should be a different point. I mean, I think I'm always tightening up my bullets. What I mean by math doesn't lie is that this is not a computational test. In other words, it isn't, if A, then B in some kind of programming language. Instead, it is the math either works and you end up with a result of a 32-bit number that allows you to have access to it, or it doesn't. And any corruption of the code isn't going to help you. You can corrupt the code all you want, but in the end,
Yeah,
you
yeah.
can't decrypt it. You're correct.
Confused deputy has nothing to do with corrupting code. Norm made a terrible, terrible mistake in naming it confused deputy because the phrase confused deputy suggests that the problem is a bug in the deputy. And if the deputy were better, he wouldn't be confused. And the real problem is the framework in which the deputy finds himself is one in which the deputy can neither ascertain nor express the distinctions needed to keep authority separate.
Right.
So it's the phrase I suggested to Norm, which he accepted but never became popular, was commingled authority. It's a problem of losing the separation between um, uh, different sets of authority, and very much the way commingled bank accounts lose the distinction between money for this purpose and money for that purpose.
Right. And we'll definitely be talking more about that in the future, in the sense that we're going to be demonstrating in a few minutes a single user version of cryptographic clubs, and and we have some solutions that allow for group delegation using Frost. That I think avoid the confused deputy problem. So we'll be talking more about that in the future. Um, so again, our choices for clubs all have to do with Schnorr. And I think, there are a couple of properties of Schnorr that are powerful that we're leveraging. First off is that signatures are indistinguishable, i.e. a single party signature is exactly the same as a multi-party signature. In all of our stack, there's no way for you to know, did one person sign it or was this a multi-party signature? Thus, simple workflows are really pretty similar to complex workflows because in the end, you're just verifying a Schnorr signature, same mathematical structure. Another aspect of Schnorr is that it has mathematical linearity, and that allows for seamless composition. So this allows us to start with basic cryptographic objects, which we are going to be demonstrating today. And these can evolve to very sophisticated multi-party protocols using the rest of our toolbox. And thus, the external systems to verify these objects don't really need to change because they all use the same verification logic and allows for, an infinite internal complexity for how these objects were created. But the verification is very simple. Uh, Specifically, as far as on composability, the primitives allow us to layer the complexity without breaking compatibility. They all use the same mathematical foundation. They all produce indistinguishable signatures. All the primitives can be combined and layered. Thus, I really want to consider them to be cryptographic Lego blocks that can fit together in a variety of ways. With Gordian Clubs, we're not using all the Lego blocks, and there are also new emerging Lego blocks that may offer incredible opportunities. But what are the Lego blocks we're using? Uh, Obviously, we're using adapter signatures, and we'll talk a little bit about that. If you're familiar with Bitcoin, the Bitcoin tweak that is used for Taproot is a form of adapter signature. Basically, the signature is modified such that if you don't have knowledge of the hash tree, you can't verify the signature. Thus, when a script paid a script hash style script is out there, and now you're actually going to publish the transaction, you have to prove that you have knowledge of the hidden values in order for that signature to be be available. But you don't have to actually reveal those hidden values to do that. You're just proving it. That's an adapter signature. And then the other area that we're leveraging is Frost. As I said earlier in our call, we had a demonstration of Frost with Bitcoin at our last meeting. But there are a lot of other future Lego blocks. Musig 2 offers sort of a trusted key aggregation and has some properties that are different than Frost that might be useful in certain situations, especially when you want to have accountability for decisions. Frost is very anonymous in the sense that even if you were a party, say you were, it was a 4 of 100, okay, and the signature passed, which meant at least four people cooperated to sign something. You, as one of those four, cannot prove that you were one of those four. That's how anonymous it is. In some cases, that's wonderful. In some cases, it's not. Musig 2 offers for some opportunities to be accountable. There is a technology called Schnorr-Blind signatures, which offers interesting privacy opportunities. Um, there's some papers I wrote at the first rebooting and then subsequently presented at a variety of cryptographic conferences for predicate logic languages that can allow for more complex conditional authorization. And they can also work in here because they can produce 32-bit random numbers or apparently random numbers that can be used to do more complex conditional authorization. We are not implementing any of that in this first implementation. But the point is we can build complex systems from simple interoperable parts, and then we can add more kinds of tools to create them over time. So our Lego block number one, sometimes is called scriptless scripts. This was Andrew Polstra who called it that. And basically, if condition X, then unlock Y. This is the mathematical proof. And it's being used all over the place for atomic operations across systems. Besides the way Bitcoin Taproot uses it, Lightning uses it extensively. There are lots of interesting opportunities with Lightning that have been demonstrated. For instance, you have the ability to create a delegatable, attenuated subscription to, say, the New York Times, which allows you to have an access for one day. Um, of somebody else's year-long subscription. And the act of using that will actually reveal the payment, the micropayment that allows New York Times to continue to publish these things. So these are already actively implemented in the Lightning Network, and I'm sure Mark and other people here can talk about how other kinds of atomic operations in other systems are being used with some of the workflows they're doing with traditional OCAPs. But I think the point is with adapter signatures, we have this elegant cryptographic composition. And this allows us the infrastructure-free logic where we can embed conditions directly into the Schnorr signatures, we can chain them, and we can build workflows that are pure mathematics. I think we have demonstrated in the basics that we can offer conditional access, delegation. I think attenuation is still a work in progress, but is definitely feasible. And in fact, I'm hoping some of this community might help us extend that. And of course, atomic swaps is already happening on other uses of adapter signatures. It allows for cross-system coordination and different kinds of delegation chains to other systems. And all the logic is expressible in math, no servers required. So you can have highly distributed systems.
Chris, you
Yeah.
didn't mention revocation.
I didn't, and we'll talk about that. So what are the limitations? Well, first off, it's limited to signature mathematics. So it is bounded by what elliptic curves can express. So in the case of Bitcoin, it's 2 to the 32 minus 766, I think, is the integer bounds there. It doesn't allow for loops or iterations. So the mathematics are finite, not computational. You can't conditionally branch on external events. The logic must be deterministic, specific to your revocation. What that means is you can, absolutely use an external oracle who publishes a secret in a variety of different ways that allows you to revoke a particular item if nobody can get access to that secret. But then that means that you do have to check that oracle. And that introduces other kinds of denial of service. But then there are interesting technologies of decentralized and distributed oracles that you can leverage. So for instance, I could set this up that it leverages a time-locked transaction on Bitcoin and basically can only function as long as that time lock has not been spent. So it's not there are opportunities here, and in fact, I think Ryan is here on the call. Ryan Grant is using this with a DID method that can leverage this. So. But it is, basically the logic must be deterministic. Also, in the adapter signature Lego block, we do not have the ability to have mutable state. Each operation creates new mathematical objects. You don't have a state here. These limitations do offer freedoms, which means if you're willing to live with these limitations, you don't have platform lock-in, you can't be censored, and you can't be surveilled. So this means that at least with the base set, mathematical certainty replaces administrative whim. The second Lego block is Frost, which basically offers threshold operations. If you're not familiar with Frost, I think it's a very important future for the next decade. It basically allows you to create M of N signatures that look like a regular single signature. They're privacy preserving. You can't tell who participated. And the verification logic is basically a simple Schnorr signature. The two core applications that we are doing is threshold signing, which is group authorization for updates. We're using the Zcash libraries for this, which have been well vetted both in the cryptography and the code. but we're also using Frost groups for group managed provenance, which gives you shared custody of version history. And we'll talk about this later, but we do not have cryptographic proofs for this particular construction, and the code has not been audited, but it basically works. So this is one of the things we're hoping the community will help us move forward on. But you don't really need to use Frost right now. You can do single party authorization. You can do multi-party, but non-Frost threshold operations, and then seamlessly upgrade to group governance when you need to. And external systems just never need to know the difference. Frost in practice, you have to have a signing ceremony. You coordinate off-chain or offline to generate the signatures. Uh, Wait, this is I'm a little tangled here. So what we're also talking here about, we also have something SSKR, which we're going to talk about in a minute. That's what's off-chain. Sorry. Um, so you have to have these signing ceremonies with Frost. The provenance chain allows for shared custody of the version history, and thus the use cases for Frost and group governance includes governance without servers, community decisions by cryptographic proofs, and you can actually design succession planning into the mathematics. But the limitations of Frost thresholds are that it does require secure multi-party communications. If you are going to do a signing rapidly, you're going to need some form of network availability. I mean, if you're going to do it with SneakerNet, you absolutely can, but it might take a while for you to move all those USB keys and into all of those places. There is a key management burden, not quite the same as private key public keys, because you do have some resilience because you don't have to have all the shares available. But it is a key secret management burden on each of the parties. Um, and you can't compose mid-ceremony. So let's say we're in the middle of a ceremony of, 4 of 9, and you've got 3 of the parties, and you're kind of desperately flailing to be able to get the fourth party to sign. You're kind of stuck if you're in the midst of a much more larger, complex system. You have to wait until you have that signature. Um, but the advantage is that you do have the freedom of from single points of failure and control, and they do allow for democratic governance through different forms of cryptographic consensus. Um, Again, this is an expanding toolkit, each build on the same Schnorr foundation. I've mentioned MuSig 2, which allows for key aggregation with accountability. We have some, initial thoughts on how to do delegation of read and write rights, but attenuation is a little more complex. I think there's some interesting opportunities in blind signatures, which preserves privacy, prevents signature correlation, et cetera. And then, of course, predicate logic. Think Bitcoin script, but simpler, where the operations are, on 32-bit numbers. For developers, I think the key point is we're building on stable foundations, already being adopted by Bitcoin, Zcash, and other projects. And these allow us to bring mathematical certainty into an uncertain world. So now we're going to move more toward the demo. We have some terms that you're probably not familiar with if you've never been. Go ahead.
Before you go on with the demo, a lot of capability systems want to have something that I guess ZCAP calls caveats. And those are explicitly ruled out, I think you said, right? The most common one is timeout. It's not valid.
I'm sorry, Alan, is caveats distinct from attenuation? Because I think,
yes,
to my mind, they're both the same.
Well, for example, an expiration time would be a caveat.
That's
so
also an attenuation.
I give you a read permission, but it expires at noon.
That's an attenuation. How is that distinct from
all right,
attenuation?
Um, all right, you can view it, I guess you can view it as an attenuation.
But
Okay.
I mean, attenuation is abstractly what you're doing, and a caveat is a particular implementation technique for expressing it.
Okay, fair enough. But it seems that since there's no conditionals based on external events, that they're not expressible here. That's the question I have.
So to be
Ah,
clear, the Gordian clubs, we're choosing all of the autonomous parts of our toolbox. But that being said, um, if you're willing to go outside of that toolbox to an oracle, you can go to a timestamp server. You could basically say this is not valid until block such and such is been proven on a blockchain.
Okay.
So there are things to do there, but then you lose some of the the autonomy. Um, but there are actually some opportunities within the autonomy. So for instance, there are these verifiable delay functions. Now, it's not useful for the specific thing you mentioned, but it's useful for it is valid when. And but the when is not deterministic by a clock. It's deterministic by a verifiable delay function where you have to prove that you've done the computation, which will require time to do. So you could, say, yeah, this is valid only when somebody is willing to expend the time in a verifiable delay function that represents, 10 days of computation. And when that computation is complete, you now can basically end up with a 32-bit number that you can prove that, yes, I did spend 10 days doing this, and thus, I'm entitled to do rotation or something of that nature.
Yeah,
Ryan?
I just want to finish the thought here. The concept is called risk adaptive access control. The example I always use is you can read this document unless the US is at war with Canada. That used to be funny, but
Yeah.
and that's the kind of thing I was looking for.
Yeah, I would love to be able to do it with predictive markets, for instance, where you can basically say, given this prediction market and cryptographic result, when the prediction market is finalized, such and such can happen. Ryan, go ahead.
Yeah, I just wanted to check, are there verifiable delay functions that are not proof of work, or is it, I guess
Yes.
maybe you could also use like a secure element, but are there other styles?
Yes. So they're basically operations. And again, this is look up VDF, verifiable delay functions. And there are a number of oddball blockchains that are leveraging this to try to get around having massive numbers of computers doing hash calculations. And basically, they're specifically designed so that they can't function. They can, in a distributed area, and that they rely on various properties of chips to do their functions. How secure they are, is emerging, but they're more than 10. Some of them are more than 10 years old, and some of the like I said, there are already blockchains that are using those in lieu of the Bitcoin method of doing
Okay.
this.
So basically anti-parallel, hardware aware, or computer architecture aware proof of work, but kind of still in that class.
Correct. And then
Yeah.
obviously you can do this with T's, you can do that with, other different types of things. There's a lot of interesting things in sort of the multi-party computation with homomorphic computation, where you can also, have some of these types of delay functions with a truly homomorphic protocol. Again, all emerging. But I think my point is ultimately at the end, it's an apparently random 32-byte number, 32, yeah, and you
Hmm.
can use it in our protocol. Anyhow, so if you haven't been to our Gordian meetings or have looked at our stack, we're going to be using some terminology that you may not be familiar with. So I wanted to go over it real quickly so that as when Wolf does his demo, you'll have some idea when he says DC bore, what the heck is that? So we've selected data structures. In particular, DC bore is our underlying structure, and Gordian envelope. On top of that, our Lego blocks that we're going to be talking about today are frost and adapter signature. We have our own identity layer called ZIDS. It is inspired by the DID standard that I'm the co-author of, but it is not quite the same. We secure our data with something called an envelope permit. We'll be talking more about that. And we have two kind of coordination protocols, provenance marks for offering provenance, and Gordian seal transport protocol, which basically allows for these objects to be communicated and the protocols to happen over any kind of connection, including sneakernet. Uh, DC-BOR is a binary encoding. It is basically a more constrained version of the IETF-CBOR construction, specifically designed to produce the identical bytes in all situations. And it is our foundation for cryptographic verification and content addressing, and it is an internet draft and being discussed actively by an IETF working group. Gordian envelope, we have a whole bunch of videos on this. We have like an hour introduction in that is really very accessible. Trying to condense it all is hard, but it is kind of a hash tree of hash trees. And it offers a subject predicate object semantic structure. And this allows us to do selective disclosure through both elision or encryption. We can reveal only what is needed and even exclude it. So like we have some situations where, for instance, we're limited to 1K if we're going to distribute a ZID or an envelope or a club through the mainline DHT used by BitTorrent. So we can basically say, well, the only important bits you need to know are this, but we're going to make a commitment to everything else. And so we're going to give you the 1K that you need to be able to move forward from here. And but we've committed to all the rest of the pieces which you can collect in other places. So this is an important concept for how clubs work. And then finally, really the most important part, and this is really how we do some of the club features and such, is that it's radically recursive. Everything is an envelope. In fact, the subject is an envelope. The predicate is an envelope. The object is an envelope. And all of the subparts of that are envelopes. So you can do these fairly radical things with this. And you might go, why would I want a predicate to be an envelope? Well, you might want to hide the predicate, elide it, but you also might want to have, well, this is the JSON LD semantic information about this predicate. No, this is the OWL information about this predicate. Oh, no, we're using this particular zero knowledge proof technique. All of those things can be in a tree of objects, inside the predicate. We've talked about the Schnorr Lego blocks. We have libraries for doing frost. We're largely leveraging the Zcash libraries. And in order to make them function, we have some simple adapter signature things. Mostly we use that right now with the Bitcoin Taproot adapter signature. Well, what is a ZID? It's a 32-byte cryptographic identifier that is derived from a key. In some ways, this is similar to DID key, except for the fact that one of the first things you will probably do is rotate that key out, because what we're really wanting is an apparently random identifier that we can prove. We have a variety of mechanisms to resolve them to ZID documents that can offer communication keys, endpoints, permissions, but most importantly, support key rotation while maintaining a stable identity. It's basically kind of the, what I would call a DID 3.0 technology. Permits are multiple ways to access the same content. So underlying in any particular object that we are encrypting, we're doing cha-cha-poly, the IETF standard for symmetric key encryption. And that basically uses a secret, a symmetric key to encrypt it. That is what we're encrypting in a variety of different ways. So we have ZID permits that allow you to do identity-based access with key rotation support. We have simple public key permits, which allows direct cryptographic access to a specific public key. We have SSKR thresholds. It's basically Shamir. You could set it up that, hey, you have to get things from three of five different places. And if you get all three of those, you basically can recreate what is necessary to get the symmetric key for the object at its heart. And then, of course, simple password permits for, you can just, stretch a password and use that and just basically share the passwords offline. But the point is you have multiple kinds of permits. I believe, like a lot of our other toolboxes, these are extendable as long as they basically reveal the base symmetric key in some kind of fashion. Um, so
I'm sorry, before you advance, I have a question.
Sure.
The SSKR thresholds, that would be the mechanism you would use for social recovery, correct?
Correct. Yes, it's basically it uses Shamir, except for the fact that it also has a second layer, a Shamir of a Shamir. So you can do things. You can do obviously 4 of 9. That's one of my favorites because it has a particular property that it is very similar to 2 3 of 3s. So excuse 2 of 3 2 of 3s. Does that make sense? We still have 9 shares. But we're saying that they're segregated so that the 3, 3, and 3, you have to cross the groups. Does that make sense?
Okay.
So
Yeah,
you can have these 3 keys be offline keys, these 3 be friends, and these 3 be family. And somebody
Right.
who colludes and gets all 3 of your family members doesn't matter because you still need something, a quorum from one of the other 2.
Yeah, it's basically a multi-cameral voting role.
Correct. Uh, and it is Frost can do some similar types of things, but the difference is that Frost never reveals the private key with SSKR because it's Shamir. Once you've got your shares, you have the key to be able to do it. You have all the information once you have the number of shares. But that does mean it allows you to do offline key reconstruction. So pros and cons. The final 2 kind of terminology from our Gordian stack are provenance marks and GSTP. So provenance marks are, it's basically a hash chain. Our goal is how do we do sequential tamper evident chains of document versions? But we're not trying to do a lot of the other things that other kinds of hash chains try to do. All it does is cryptographic link the content digest to the previous mark. So you're starting with a Genesis mark, the 0 mark. You're progressing to number 1. You're progressing to number 2 in a continuous chain. But we are not trying to do like what Git does when it does its own provenance of also saying, oh, it has to be a diff of the previous version. You could literally have completely discontinuous objects that you are basically saying, I'm making a statement about this, and it is provably after this statement. But it's not making a proof about time, it's making a proof about ordering. Okay.
Christopher, I think one of the things we forgot to mention on this slide is that one thing that does make provenance marks unique is that each provenance mark includes a pre-commitment to a secret that has to be revealed in the next mark. So it's not just a backwards-looking chain. In fact, the backwards-looking hash or whatever which we use in clubs is optional, whereas the forward-looking commitment is intrinsic to it.
Right.
Hmm.
And we've done a lot of. Go ahead.
Does the forward-looking thing? I hadn't heard about this before. Does the forward-looking thing prevent branching or inhibit branching?
Not necessarily. It depends on what, it's possible to branch it, but then the question is, how do you decide which is authoritative? What part of what makes just, if you're going to use simple forward branching, we discussed this in our previous talk, so I don't want to go over too much of that because we did do a recent talk on provenance marks. But part of what makes provenance marks secure is a number of people who are replicating a chain in a kind of a distributed way, so you can actually cross-reference them. And so if whoever holds the seed that generates the provenance mark, or even a frost quorum, which is what we're developing now, tries to branch it and then tries to publish branches of it, then that gets flagged by the community of whoever's archiving the chains as not allowed or allowed, depending on what the protocols are you built on.
Okay,
It's just a building block.
So if you have disjoint audiences that can't compare notes, then you can still branch.
Correct.
Yes. Yeah. Well, in fact, if I issue a provenance mark and nobody has ever read it, I can issue another one on top of it that's different. So it's just that when it becomes a settled consensus, that it becomes very tamper evident, and nobody else, other third party who does not have access to the seed that generates the whole chain, or in the case of Frost, the Frost quorum that generates the whole chain, can actually create the next mark.
Right.
Okay,
And there
great.
are other Lego blocks that use Schnorr that we could, use in the future that might allow for, the provable reconciliation of branches and things of that nature. None of them are solid enough or easy enough that we want to use them right now. That being said, within the context of the Frost provenance mark, a lot of it has to do with the nature of the quorum. If you have a quorum that is a majority or a supermajority, then it's very hard to fork, because if you're going to require 66 of 100 people to cooperate to advance the mark, well, clearly that has the majority, and you can make statements about that majority in a variety of different ways, such that that it requires them, 66% or 67 votes to advance, and thus can give that one priority of a different quorum. But clearly there are sometimes advantages to forking. I mean, you could have a 4 of 100, where it's basically, as far as we're concerned, when we set this up, only 4 people need to agree to advance this provenance mark. Clearly there are lots of sets of 4 people out of 100 that could advance it. And it's, not our the responsibility of the underlying cryptographic club object to reconcile that. We also have a variety of different user interface tricks and other different types of things to make it human readable, to use it with our some of our QR and UX stuff to allow for provenance marks to be used in a variety of other circumstances. But in the case of clubs, we're using the full version of it. Finally, we have GSTP, which we're not going to be demonstrating today, but basically it's a secure multi-party coordination that's transport agnostic. And this is what allows us to do the sneaker net type of things. The particular feature of it is that in a multi-part protocol, it's stateless, in the sense that if you have state, you basically encrypt your state with your keys, encapsulate it inside what you're passing to the next party, such that when they pass it, they can't decrypt it, but is their responsibility, if you're going to continue the protocol, that they pass it back to you so that you can decrypt it and get the state you need to proceed in the protocol. And I think
that state is self-encrypted and self-signed, so it's what you sent yourself into the future, essentially.
Yeah. So it basically offers a lot of interesting secure coordination without infrastructure opportunities. So you need to understand these to understand Wolf's demo. Basically, he's going to create a club using a ZID. The ZID identifies the publisher across updates. The content of that ZID is stored in a Gordian envelope using DC-BOR. He's going to demonstrate multiple permits that allow different access methods. Later, if members make decisions, the Frost threshold signatures can authorize additional updates. Provenance marks create tamper-evident history of the changes in the new editions, and GSTP coordinates secure communication between the members. The result, an autonomous cryptographic object, no servers, no databases, no central authority. Mathematical proofs replace administrative control. Unstoppable, private, censorship-resistant collaboration. Again, it's a layered onion. The envelope is the DCBOR encoded structure. The public metadata is the visible information that is non-encrypted, the club ID, the version, provenance details, the encrypted payload, which is the actual club content and member data. The access layer is the collection of permits, and the governance layer inside there is what are the rules for the signatures and provenance chains, et cetera. Right now, we are supporting read and write access. There are various kinds of other permissions that could be granted. We are not really trying to explore that right now, but the OCAP community may have additional ideas here. Basically, read access gives you the ability to decrypt and view the current club content. The multiple permit types allows for different access methods. I mean, one of my favorite access methods of Mark's at Xanadu was the knock club, which is basically you knock and you get in. It's just all you have to do is ask. So you can have something as simple as that. And you can have one-time or ongoing access depending on the permit type. And then the next step up from that is write access. This is what, go ahead.
When you say one time, that sounds like mutable state, that once you've used it, you can no longer use it.
Sorry. One per edition. So
okay.
I could basically, by how I encrypt the internal object, when I do the next edition, I will, the best practice is you're actually going to change the symmetric key for that particular edition. You're going to make a commitment to the content. But you can choose not to, which means the people who had access to the previous edition will still have access or privileges on the new edition because the symmetric key that is revealed is the same in both cases. Also, public key, there's some public key things you can do. But the point is, we're not saying one or the other. It is a design choice per club. For write access, obviously you have to be able to sign, but you also need to be able to do a provenance mark. So you're really, having to know two secrets. One, which is the seed of what you're using to generate the keys, or the ZID details, and the provenance genesis seed, or the shares in a frost quorum that allow you to participate in generating the next value. So the point is, you have to ensure ordering in order to prove that you had write access. Key concept, flexible governance while maintaining security. Again, unblockable, perfect privacy. It's usable in disaster resilience scenarios, internet outages, infrastructure failures. No authority can revoke these mathematical proofs. If you have the secrets, you can do this. Thus, the control rests with the key holders, not any platform operator. Can't be algorithmically suppressed, can't be deplatformed. Mathematical certainty replaces platform dependency. Why might you use this? Infrastructure can't be trusted. Dissidents organizing without surveillance. Long-term archival that outlives companies. Emergency coordination during outages. Mathematical proofs that can endure when servers don't. So Wolf's going to do a demo. He's going to show you identity setup. He's going to show how the Genesis edition is created for the provenance mark. He's going to demonstrate some access methods, some addition updates, and then the verification. What you'll want to look for is this self-contained artifacts working without any infrastructure. He's going to do the demo, and then afterward, we have an opportunity to discuss some of the cryptographic constructions of how we're doing some of this. He is going to be showing SSKR, which is the 2 of 3 threshold. Again, Anybody who can get the 2 shares can reconstruct the decryption key. But once you have it, that's not revocable. You have it, and you have that now forever, which is different than in the case of Frost. Ultimately, this is what the encrypted object looks like when it's encrypted, which you can see almost all.
Could you make
Sure.
the font larger on that?
Sure.
There will be other versions of this during the demo as well, where it will be larger.
Okay.
Yeah.
And this is just to be real clear. This is the text representation. It's called envelope notation. So it's not JSON. It's not CBOR diagnostic notation. It's envelope notation. Like I said, I go deeply into this in our other videos and talks and papers on envelope, but this is basically showing the hierarchy of the subject, which is encrypted, and then a set of predicate object assertions on that object. And then that's all wrapped, and then you see a predicate object assertion for the signature.
So all of this is using our command line interface. So the Club Edition Verify is what proves the authenticity, and then you can do sequences. He's going to show the content decryption and the provenance progression. This is in the Club CLI Rust demo in our repository. You have the foundations, I hope, to understand the demo, and I'll turn it over to Wolf.
Great. Thank you, Christopher. So I'm going to share my screen here. Okay, so you should be seeing my Visual Studio Code window now. And what you're seeing at the top is a markdown file called demolog.md. At the bottom, you see my terminal. That's all we really need for this. There are several tools that I've installed, which are all in our stack and all available. If you're familiar with Rust, our tools are written in Rust, and so our tools are all installable using the cargo package manager from crates.io. I'll be using ZSH for this demo. So I'm going to set basically I'm hitting Control Enter on these lines here, and that just tells VS Code to retype the line and execute it in the terminal. So I'm going to be doing a lot of that in this, and but basically in this log, you'll see in this case, for example, I'm just looping over the names of the required tools here: Cargo, which is obviously installed with Rust; Envelope, which is our Gordian Envelope Manager command line tool; Provenance, which is our Provenance Mark command line tool; and Clubs, which is the new tool that we're going to be mainly talking about here. Like I say, we've done previous talks, extensive talks on envelope and provenance marks, and I urge you to check those out. I'm happy to answer specific questions about them though as we go. But the first thing this little log does is it just shows you the versions that are installed, so we can double check that you have the versions installed that we have published. Then we have a directory here, which is let's see, this is the code of the Club CLI directory. So this is the Club CLI tool. This is the demo directory. It's only used to store the state of the provenance mark generator, because you need a private seed for that, as well as it keeps a history of your marks. But the generator, which stores JSON here, the seed is a randomly chosen number that's encrypted here, and you never give it out. So it has the same kind of risk profile as a private key, which of course part of what using Frost to do this is that spreads that across several people in a governable way and less risky way. So, but I'm not going to dwell on Frost in this demo. This is single publisher, many receiver. So, but this basically deletes that directory and recreates it, so we have a place to store that. So the next thing we're going to do is the publisher is going to spin up its cryptographic material. And this is done in several steps. We use the envelope tool here. We use the subcommand generate private keys. And then we're going to echo each of these to the terminal. I'm going to do these all at once, and then I'll talk about what we're actually seeing here. So I'm going to select these lines, Control Enter. And what you're seeing at the bottom is essentially the same thing you're seeing at the top. So I'll primarily stick to the top, even though I want to demonstrate this is in fact working. So what you're seeing is when you see a UR, this is our basically our ASCII armored binary. This sequence here, and if you go into again, we've done demos and talks and so on about this. The baseline is actually human readable words called byte words. What did I just do? Oh, okay. So I just went to the bottom of the file. That's what I did. Okay. So each two letters is basically the first and last letter of an English word. There's 256 of them. That's what they're called byte words. So a UR is basically a way of, it's called a uniform resource. It's a way of specifying tagged CBOR, essentially. So if you're familiar with CBOR, this is just a tagged CBOR object. This is a specific kind of tag, and this is the type of tag that represents the CBOR tag, which is crypto private key base, which is basically just key material. And this is the actual ZID document in this case. Now, what you see below it is the unpacking of that. Then that was basically the envelope format call here with the publisher ZID. So it took this and transformed it into the human readable form here. The subject of the envelope is the ZID identifier itself. It's a 32-byte number, even though we only show the first 4 bytes for brevity. It contains one assertion, which is the public key, which also includes the private keys. This is the private ZID version of the ZID document. This is not what you give to other people, which would elide the private key. And that's part of why we salt it. That way, it's decorrelated. Somebody could guess all day, and they still wouldn't have reveal your private key because, again, this is a hash tree here internally. So we protect your private key so that when you elide this branch, all you get is the elided branch. You get a hash, but it's a salted hash. So you don't even have, even if you guess the private key, you wouldn't have that salt. And then we have blanket permissions. This ZID is allowed to do anything this ZID is allowed to do. So, which is, basically everything. If you trust this ZID, then you trust everything it will do. Then this is part of our delegation hierarchy protocol. All right. So the next step is that now that we have the publisher's information, private key, we're going to create 2 readers who will be permitted, specifically Alice and Bob. And so Alice basically is going to do the same thing: generate private keys, generate the public keys from the private keys, generate a new ZID document from the private keys, and then format that. There we go. So this is Alice's new ZID document. And then we're going to do the same thing for Bob. All right, so now we have 3 participants: the publisher, Alice, and Bob, and they're fully kitted out now. So the next thing we're going to do is the publisher wants to create a new edition, the first edition in their club. To do that, they have to have the content of the edition, which is going to be a Gordian envelope. And as you see here, they're going to take the actual payload, which is a string. Now, a Gordian envelope can be as simple as a string, which is just a tag, and the string itself is just the whole Gordian envelope. The nice thing about Gordian envelopes is it's a very elegant, very minimal structure that allows branching, and so that with just a few additional bytes, you create an assertion on that as well. And every part of this, the predicate, the object, the assertion as a whole, the subject, and the envelope as a whole, has a unique digest because it's a tree.
I'm sorry. Could you, in terms of which parts are the subject, the predicate, and the object, could you point out explicitly that again?
So when you see if you just see like a string by itself, that is the subject of the envelope. It has no assertions. There's no predicates or objects. And that's what we do. That's what we do the first command here: envelope subject type string, and then we give it the string, and that creates this first thing. And then we format it so you can actually see this is the UR form, this is the transportable form, this is the human readable form. It's not designed to be round trippable. It's just human readable. The next thing we do is we say envelope assertion, add predicate object string title. This is the predicate, and string Genesis edition. So we're basically adding a single assertion to this subject title Genesis edition. The third thing we're going to do is we're going to wrap that envelope. That's because when you add a signature to this, it only signs the subject. So if we signed this right now by adding a signature, we'd only be signing the subject, which means this assertion wouldn't be covered by that signature. So the next step we're going to do is we're going to wrap it, and that's envelope subject type wrapped, and we pass that previous going to it, and now it's wrapped. You see the outer curly braces. And by doing that, we can add assertions to this, like the signature, or basically take its digest, which is the most important thing we're going to do with this right now, which basically means, and the thing about envelopes, which is a little bit counterintuitive, but it's one of the superpowers, is when you elide or encrypt an envelope, it encodes its digest in a way that's undeniable. For example, the digest of an encrypted envelope is stored in its additional authenticated data. So you basically know what the digest of the plain text is without without decrypting it. And of course, if you care about the correlation, then you can salt it and so on to decorrelate it. But you'll see that in a moment.
Yeah, also everything, all of these pieces underneath themselves are envelopes. So for
Yeah,
instance, that title and Genesis edition themselves can be a Gordian envelope.
yeah. Yeah, exactly.
Yeah.
Well, in fact, they are Gordian envelopes, but they have no assertions on them. If you saw assertions on them, then you'd see additional pairs of brackets or curly brackets that would
Actually,
indicate that this is structure.
could you do that? Did you um, just show us an example of what it's like when it's nested in that way, and in this readable
Yeah,
notation,
right.
structured
Well,
notation?
here the ZID document itself, the ZID, which is just a 32-byte number, a tagged CBOR 32-byte number, has one assertion, the key assertion. That key assertion
Okay,
is a public keys
good,
object. That public keys
good.
object itself has one assertion, which is the private key object, which itself has an assertion, which is the salt. Actually, two assertions.
Oh,
The first one is the private key assertion, which has an assertion, and the other one is the all assertion. So it's two assertions. This assertion as a whole has another assertion on it, which is the salt. So
okay,
when you
excellent.
light a branch, you basically, the digest takes everything into account because it basically uses the serialized DCBOR, which is one of the reasons why we use DCBOR, which is deterministic CBOR, because we want the same semantics to always encode to the same byte stream. So when we take digests, we can be assured that if you put the same semantics in, you get the same digest out. And we
Where's the
basically,
closed curly?
so the closed curly here, there's two of them.
Oh, there it is.
Yeah,
I'm sorry.
yeah, there it is.
That's the one I was looking for.
Yeah, this basically shows that the assertion itself is what we're placing this assertion onto, as opposed to just putting the assertion on the predicate or the object, which would look different.
Right. What the textual notation you're using here
Hmm.
with the square brackets and the angle brackets and
Hmm.
the colons,
Yeah.
ki- it's clearly not JSON, but
No, it's not.
it seems to be conveying information that's sort of similar
Hmm.
to JSON. Is it YAML or is it
Nope,
something
it's what we
else?
call envelope notation. It was developed for Gordian envelopes.
Okay.
We discussed it
Okay.
extensively in both our videos and so on. But basically, it's designed to be a form of diagnostic notation. It's not designed to be round trippable. Like I say, this is
Okay.
a 32-byte number, but you only see the first 8 bytes for recognition
Okay.
because it's designed to be diagnostic. Um,
Okay.
Now, so we're going to actually now
Ryan,
execute.
did you have a question? Sorry.
Yeah, please.
Yeah,
I'm not looking at whose hands are
briefly,
up, so please just
I
speak
don't
or.
know yet why assertions and predicates are a valuable distinction. I think that theoretically it makes a lot of sense, but I'm looking at the objects and thinking, well, I could just kind of ask for one predicate or another predicate, right?
Yes. I mean, well, the idea is you have it basically goes back to the semantic web idea of yeah, of subject predicate object assertions. But the idea is that you're going to have a subject about which you make a number of assertions. The subject can stand alone with no assertions on it. You can also make a number of assertions on what's called the unit object, which the unit subject, which carries no content. So it's up to you to decide how to use these things. We have kind of conventions we've developed as to how we use them. So for example, in this case, the actual this is like the title of the edition. In this case, where or maybe this could be like a newsletter, and this could be metadata about the edition, which is the title. And so our APIs, they let you query these by various criteria. And in fact, we have a regex-like pattern matching language that you can also use in one of our crates that lets you actually match on various parts of the hierarchy of envelopes. So,
But also to be clear, we are not doing JSON LD here. There is not, any semantic content, semantic details are optional. And you would basically, you can do those by turning a predicate into adding additional predicates and objects to the predicate if you need to. But
you
this is
can.
not JSON LD.
Well, also I should note that rather than have to do that, we also have noticed that some of these things are double quoted, like these literal strings. Welcome to Gordian Club. Other things, sometimes you'll see single quotes. These are what we call known values. We have a registry of known values, which are essentially they substitute for like a long URL you might want to include from an ontology of some kind, because if you and what the even though it's produced here in the envelope notation as a string, a human readable string, it's actually just an encoded up to 64-bit number. Of course, it's a variant, so it doesn't take up much space if it's a low number in the actual encoded CBOR. So you don't have to encode all these strings. When you see a single quoted string, it's just a number. But it's a known number, so people can register them. Eventually, we'd like to see all the major values from various ontologies in our registry. And that way, you can basically represent all the things you can do with, JSON LD and OWL and all that in Gordian envelopes without taking much space at all.
Okay, so basically, it's for classical semantic web ideas.
Yeah, it's classical semantic web idea, but it's basically opt-in. So, an envelope can be any DCBOR object, or you can, obviously DCBOR objects can stand alone. When you see an object like this is just a tagged DCBOR object. This is a known tag, and this is basically just a hash of the private key. So, so our stack basically, has knows a set of known tags, and then we'll produce it in the Gordian envelope notation when it sees this. It could just output the DCBOR straight, and then you'd see the private key. But envelope notation doesn't do that by default. And in this case, it's a salt. You don't care what's in it. You just know it's a salt object. But this is a leaf node of the envelope that is tagged CBOR, which is a salt tag with some random data in it. Whereas this is, for example, this predicate is a known value, a number, and this is also a known value. The object is known value, which represents the idea of all, granting all permissions. And if you look at our registry, you'll see these all enumerated there, along with what their exact semantics are.
How is the registry administered if there's two conflicting requests to add something to the registry?
Well, obviously, the governance of this is very nascent at this point. I administer it basically, and I'm the only person who's actually registered data in it at this point. But we want to make it very open. Eventually, we probably would delegate it to IANA when they're interested enough in this kind of thing.
Okay.
So yeah, there would be a more complex governance structure set up as more people want to register. But obviously, it's a 64-bit space. It's very large. There's enough room for everybody.
Okay, so it becomes a central point of it's a centralized coordination.
Yeah, for assigning known values. But of course, if you want to assign keys, these can always be strings you assign as well. So there's no reason why these have to be known values. They can be anything you want. Again, these are envelopes, which means they can be literally anything. Known value is just a tag we registered with IANA that in the CBOR tag register that says these are known values and these are administered by us. So it's basically a tag with an integer in it that is administered by us. And eventually, like I say, we'd like to delegate that back to IANA or some governing body.
Okay.
All right. So now we're going to actually do this multi-step thing to actually create the content that we're going to publish as part of our edition. All right. And there you see there's the wrapped subject with a single assertion on it, and it's been wrapped. That means when we take the digest of this, it'll be a unitary digest, and that'll be important. So now we're going to capture the content digest. So that we say envelope digest, and we pass the content wrapped, and that gives back a UR digest, which is the digest of that branch of the tree, which is the top level of that content. And there it is for our thing. And you notice that it's actually identical here and here, because there's no variable data in this. It's all deterministic. This is just a known set of values here, so it's always deterministic. Whereas other things like signatures may not be deterministic depending on the how you sign. Provenance marks have a date encoded in them, so they may not be deterministic unless you fix the date. So you'll see anyway. So now we're going to start the provenance marks chain. So the provenance mark chain basically is there's the first mark in a chain is called the Genesis mark after the Genesis block in Bitcoin. And it has certain attributes which are checkable. You can always recognize a Genesis mark. It has no predecessor, but it also commits. That has that secret. It has a hash which commits to a key, which is a number which will be revealed in the next mark. That's the pre-commitment. Anyway, that's all under the surface here. We're going to do the first line, which actually uses our provenance new. It's going to tell it where to store that. It's going to give a human readable comment that will just be stored in the JSON. It'll be output in the format UR. And we're going to encode that digest in what's called the info field. This is hashed into the mark, and therefore the mark will be bound to the content of this edition. We're going to echo that out, And then we're also going to tell it to a printout of the provenance mark in a human readable form. And here's the UR of the provenance mark in the test run. You see it's similar down here. And then this is the markdown that I would, for example, if you actually go to provemark.com/wolf, that's provemark, PROVMARK.com/wolf, you'll see my personal provenance mark chain, which I use when I think I do something original. I actually I have a provenance mark chain that I manage personally, and then I publish this markdown version of it and link back to it from wherever I'm publishing on X or whatever, if I think I do something clever. But this is a new chain we've just created. This is the Genesis mark. This is the kind of the byte words identifier of it. It's not the full mark. But it's unique enough so that you could search for it in a large database and be very unlikely to get a hit. This is even a more kind of subtle form. This is using what we call byte emojis, where we have 256 curated emojis that can represent bytes. And again, this is just for human recognition and searching. This is the actual full provenance mark, which includes the hash, the key from the previous mark, if any, the sequence number, the date, all those kinds of things. Again, you'll read about that in my other presentations. So now
could you explain again the thing that's highlighted there, the sequence of icons?
Yeah. So there's four bytes that when you actually read the paper on the provenance marks, you'll see that there's we actually obfuscate the actual, even though the provenance mark is not encrypted, it is obfuscated, so it basically becomes a sequence of random bytes, and we take 4 of those characteristic random bytes and use those as a recognition key. In this case, each of those bytes is being transformed to the corresponding byte word. Again, there's 256 common 4-letter English words. And they have certain attributes, like the first 3 letters are always unique, the last 3 letters are always unique, and the first and last letter are always unique. And what you're seeing in these URs is a sequence of like IH is the word, is the unique word that has the first letter I and the last letter H, but it's one of exactly 256 curated words that have a number of things that make it very easy, for example, to just say paid judo beta user and be very clear which 4 bytes you're speaking of. So our common denominator basically is human voice or writing in terms of the minimal way. Obviously, it'd be very tedious to transfer something this large that way, but you could do it. But we also, for like, you'll see that in my provenance chain and on X and so on, I'll just sometimes put this at the end of one of my posts. And if you recognize that we always use the filled circle P for our provenance marks, then you'll recognize that these 4 things after are essentially these same 4 bytes, but transformed into a different set of curated emojis that are designed to be, highly recognizable. You use like a maximum of two bytes and things like that. So again, designed for transportability. You'd use this when you want to be very terse. You'd use this when you want to be a little bit more explicit. And if you want all the data, then you just embed this, which is probably too much for a tweet usually. So.
Okay.
The key point is that these are not, cryptographic values. These are for the user experience. Like, how do you look up something? How do you compare 2 things side by side? We also have a thing called a life mark.
Life hash.
Life hash, excuse me.
So let's go to lifehash.info.
That basically allows you to have a sort of a visual identifier. We're trying to solve the problem of everybody going I'm carefully reading the last 4 digits of the hash and I'm trying to compare it against this, and it's kind of hard to do. What we do is by having heterogeneous methods by which to compare these, you can go, whoa, wait a second, that is not the same life hash or provenance mark that that this other thing says it should be. I maybe should investigate further.
And one of the earliest problems that Chris and I tackled together when we started working together quite a few years ago now is, how do you recognize digital objects? How do humans recognize digital objects? Because it's very easy, obviously, even in like a SHA-256 hash to not be able to compare them correctly or to find near misses, through a search that could fool a user. So how do you recognize in reliable ways digital objects? And so we came up with life hash and byte words and now byte emojis as a way of basically taking digital objects and in standardized ways, creating human recognizable versions of those things. And in some cases, like this could be used as a search key in a large database, be very unlikely that it would collide with anything else. But even if it did, then you'd still be able to reference the provenance marks it came back with. Same thing with Bitmojis. So, and again,
So,
Mhm.
so I mean, there's been attacks that I'm sure you're familiar with on the user interface side of these systems,
Mhm.
of maliciously creating a key that has the same first four letters and the same last four letters.
Yes, yes, and that's very
Understanding that,
difficult to do with our case because you can use any of these things together. You can use, for example, a life hash and a byte words hash. You want Bitmoji hash as well. And so the idea that you could create one that maybe gets close visually to one or gets close in terms of the actual words of one, but getting them all impossible.
Yeah.
And then
So
maybe
it's we're
they're all
big believers around heterogeneity and these types of things. So we still show, things like the first and last four bytes, and we have this whole user interface convention called an object identifier block. But we should probably move on because we're now at 11:30, and I know
yeah.
some people had to go.
I'll
So
try to
let's.
speed it up a little bit, but one other thing before we go: the last four bytes, the last four byte words, that is the last four 8 characters of a UR, are also a, uh, uh, a CRC32 of everything else. So you can always see if you're looking at the
wow,
same UR by looking at the last 8 letters of a UR. If they're the same, it's the exact same rest of the content. So you know that just by looking at it. You don't have to compare them, the whole thing. Um, and if they don't match, then it doesn't decode. All right. So now, we've got our provenance mark that we're going to embed in our addition. So now this is the actual, we're going to call the clubs tool. We're going to create the first edition. We're going to pass our publisher's ZID in, which includes its private key. We're going to pass the wrapped content envelope. These are all expressed as URs, UR ZID, UR envelope. We're going to pass in the provenance mark we just generated, which is UR provenance. We're going to permit this to Alice through her ZID, which we only care about her public key in this case, because we're going to encrypt the symmetric key to her public key. In fact, this is Alice's whole ZID document. This is Bob's public key, so you can use either, basically. And then we're going to actually also generate a 2 of 3 SSKR split. This is sharded secret key reconstruction. So this is the Shamir that Chris was talking about. And then we're going to basically capture that in a shell variable. Again, we're not using stored files for anything but the provenance marks here. We're capturing everything in shell variables here. So there it is. There's our envelope, and then and then notice that what's happening here is we've printed out. In fact, I'm going to turn out line wrapping off so we can see. We've outputted 4 envelopes here. The first one is the actual full new edition that we're going to publish, and the remaining 3 are the 3 shares. They're just the symmetric key of the content that's been split using SSKR. So if you have this and any 2 of 3 of these, because you distribute them to parties you trust, and if they actually agree, this is like their vote. If 2 of these people give these shares to a third party, that party can decrypt the content. And they themselves may not have the ability to decrypt the content,
Right.
but they can
Or
decide
these
to
could
hand the
be
show.
put on an NFC card such that you put one in your bank vault and one at your mom's in Canada.
Right. So now what we're doing is we're just printing those out. So we're basically showing, okay, here's the envelope UR, here's the actual, this was shown in the
Right.
presentation, but smaller. Yeah. So this is a wrapped envelope which is signed by the publisher. Inside the envelope is an encrypted subject, which is the content that we showed you earlier. It has a type identifier. This is a known value. This is an addition. This is not a registered value. This is just a string, but you can this is one way of typing envelopes essentially without having to have assign a separate UR type. This has an assertion on it, which is the has recipient, this is the actual encrypted symmetric key encrypted to Alice's public key. And here's another one. In this case, because it was given a ZID document, it actually is identifying the ZID, but that's optional. You don't have to actually identify who it belongs to. And in the case of Bob, we didn't bother. And then the club is publishing this, and this is what you would dereference if you wanted to, for example, get the club's public key, because there's no club public key here. And so part of what we are presuming is a way of dereferencing the pure ZID to get the ZID document, which includes the current permissions and public keys. And ZID documents are also published in a chain using provenance marks. So you can always find, if you're assuming you have a resolver network, you can always find the authoritative permissions of what a current XID is allowed to do, who it's delegated permissions to, what its current keys are, how, and so on.
And you could also embed it if you wanted to. So you
Right.
could also put the
you could put the whole
DID
ZID document.
document.
Yeah, you could put the whole XID document there here, but then you have to trust that it is what it is rather than going back to a resolver network that might be have vetted things more carefully. And then we have the provenance mark, which is basically the provenance mark we generated previously. That in its info field also has the hash of the encrypted content. So so basically, and again, this has to be generated in a particular sequence. It can't be generated out of sequence. And then we're seeing basically the SSKR shares are also simple envelopes that are the encrypted symmetric key along with an SSKR share, which is just an object that includes what's needed to combine through the Shamir algorithm, our multi-level Shamir algorithm. And so, and again, 2 or 3 of these will retrieve the symmetric key you need to decrypt the content. So now we're going to actually verify the composed edition. So this, if you receive an edition and you know the publisher's public keys, which are included in the ZID document here, then you can verify that in fact it is a valid edition by that publisher, and basically no output basically means success in this case. So now we're going to basically extract the 2 permits because we want Alice or Bob to be able to decrypt the content. That's what these lines do. And again, this is what the sealed message looks like as a UR. And then Alice basically wants to decrypt it because she's part of the audience, but so she has to use her private key, but she doesn't know which of these sealed editions. She could use the ZID attached, but that's just metadata. It may not actually be correct. But so she's going to, this loop here is going to try for each of these 2 permits. It's going to try to decrypt the actual content. So I'm going to execute these lines here. As you can see, it found the envelope, and basically this is the actual decrypted content that was decrypted by Alice using her permit. And then the SSKR shares, we can show that a quorum of shares can recover the same plain text without any permit, or rather using the SSKR permit. So in this case, we are using clubs content decrypt. We're passing it 2 of the 3 SSKR shares. And then we're basically printing that out both in UR form and envelope form. And there it is. And then we're going to basically create a second edition. That is a new thing. And this could have a different set of permits. Somebody asked about revocation earlier. This is what you do with revocation. You drop somebody from your permits, or not distribute your SSKR shares to that person in the future or whatever. So that's what and basically, so reading is basically having a permit that reads the edition. Writing is basically having the authority to actually create the provenance mark and signatures. So in this case, we're going to create a new subject with we're basically doing the same thing we did with but creating a new content envelope. So this is that we're going to publish as our second edition of our club. There it is. We're basically going through the same dance we did before. We're going to retrieve its digest. We're going to create the second provenance mark, and this again necessarily follows the first one cryptographically. That's what that one looks like, both in UR as well as markdown form. And then we're going to create the new edition, Clubs Edition Compose. This is not the init call. This is the we're going to create a new edition here, along with the same basic permits in this case. We get the new 4 envelopes, and then we distribute them as appropriate. Review the second edition envelope. Again, this is the same idea here. This is the 3 shares and the envelope. The subject, the content is encrypted again. We're going to verify that. And then the new step we're going to do after this, that succeeded, is that we're going to confirm that both editions belong to the same club and form a continuous chain. Editions may be provided in any order. No output indicates success. So in this case, we're passing both editions, and we're passing them, in fact, out of order from the issue that they were published because the provenance marks are used to order them. And so no output here being success is that they are, in fact, from the same club and that they form a continuous chain. It would warn you if, for example, the chain is broken or any of the things didn't validate or it didn't start at the very beginning, so which you may or may not care about. But it definitely in this case indicates that these are both the entire chain from the same club with the provenance marks unbroken. That's the demo.
Thank you.
Mhm.
I'm gonna go ahead and go to the slides.
Yep.
And uh, so that was the demo from Club CLI Rust, which uses Club's Rust and our other repositories at Blockchain Commons on GitHub. The other thing particularly to note is that his testing methodology basically you can run a single Python script and it will basically run that entire sequence of things, and thus you can create your own, demos of these, of this workflow in a variety of ways by modifying that object. Is that correct, Wolf? Oops, you're muted. Wolf,
Sorry
you're
about that,
muted.
Christopher. Yeah, sorry about that, Christopher. Would you repeat the question? I was actually AFK for a moment
Yeah,
earlier.
you basically in the Club CLI Rust repo have a Python script that runs that entire demo, and then if you want to experiment with other different types of things, just modify the
Yeah,
Python script.
absolutely. What you saw there as a series of command lines was actually generated by a Python script that meta generates that and then you run that Python script and that actually generates that markdown output that I just showed you. So you can tweak that, and that's included with the repo with the Club CLI repo as well.
So again, Club's Rust, which does edition creation, frost signatures, permit handling, etc. And then the CLI Rust, which is what you saw used as part of the CLI demo. Um, Obviously, to install them, cargo install, envelope CLI, provenance CLI, Club CLI, and that particular
That's the direct link to the demo I just showed you.
right. So future work, obviously using Frost for additions. So basically in this case, we're using the symmetric key to encrypt the addition content and then make a commitment to the next provenance and a mark in the chain without having to have that Genesis secret seed. It's collaboratively created and then sign the addition Gordian envelope using Frost. So we do have a proof of concept code working for this. And it's I think you said it was a minimum of 3 rounds per. Is that
Yeah,
correct?
there's 3 frost rounds needed, one to generate the encryption, the symmetric encryption key for the content, one to generate the provenance mark without a seed, and one to generate the signature for the entire envelope.
Um, Once we have that more fully integrated into our libraries, this will allow Frost groups to publish editions in addition to our the technique that we just showed you, where a single user publishes an edition. Um, and then in order to do that, we need to create a server right now we call Hubert, which is a dumb message passing hub for GSTP messages. It basically receives the Gordian seal transport messages and supports multicast, single cast, store and forward, etc., without actually having to have any knowledge of the what's going on. And this will simplify the communication needs for Frost to produce new editions. Um, so we basically already have working libraries for Frost and for GSTP. We just need to integrate them into code for Gordian Clubs. So it's not a technology achievement as much as it is just integrating some of the pieces we already have. Um, Now, what you saw was static permissions via permits and signatures. A number of you have come here because you're interested in the object capabilities opportunities, where we can delegate authority without sharing keys, do attenuation, composition, etc. So these are research phases, and really before we can go to any kind of deployment. These novel cryptographic constructions are going to require formal proofs. So we're really hoping that this will attract interest in people to, not just, engineers, but, cryptographers to take a deeper dive into, what we're doing. So specific for OCAP delegation without key sharing, Alice wants to delegate her read or write authority to Bob, but she wants to do it without sharing keys and without creating a new edition. What I'm going to give you in a second is what I call the naive version of it. What do I mean by naive? We've known that Schnorr aggregation, back when it was first created. That was one of the things that was wonderful about Schnorr signatures was they could be aggregated. But if you do it in the naive way, it can leak keys. Thus, it took another decade for MuSig2 and MuSig-DN and Frost and other protocols to do these without some of those attacks. Thus, we're going to need cryptographic proofs before production use. But the naive version, basically, Alice creates an incomplete signature. She generates a random secret and commits to it. Uses the symmetric key for that to create an adapter signature that only Bob can complete. Bob has to have he's published his public key, which Alice has used. He can use his private key to complete the signature. Completion, the secret reveals the secret that he can then use to have the read authority to decrypt this edition. So no key sharing symmetric key sharing is involved just the public keys. Alice retains her initial access. Basically, the complete signature hides the secret that unlocks the decryption. So it's a cryptographic lockbox that only Bob's key can open. A little bit more sophisticated is Alice with write access wants to delegate to Bob without sharing keys, symmetric keys, or updating the current edition. Obviously, anybody could basically share the symmetric key of the object with the future party, or share the Genesis keys and the commitments and things of that nature. There's nothing that stops people from doing that. So, but this is about how you use public key operations to do this. So we're basically doing a standard Schnorr, and then we're tweaking it for the adapter signature that is locked to Bob's public key, which means only Bob can use this with his private key. And it proves both that it was used with Alice's authorization and with Bob's identity. This results in a delegated write authority. Bob can create a new edition, but it shows Alice's valid signature. No key sharing is required, and Alice still retains her original authority. So basically, this gives Bob a blank check that only Bob can fill out. So those are what I call the naive constructions. The harder one here is the Frost provenance mark. So Frost came out in 2019, and at this point has a lot, hundreds of papers, examining it and building on it and whatever. So we are very confident with the underlying Frost method for doing group signatures. That being said, we want to use those same signatures to allow for a new edition of a provenance mark, which is a unique, unpredictable symmetric key that everybody can verify came from this group. We have a particular construction using a VRF where the group shares a secret that no individual knows. Each document creates a unique mathematical challenge. The group collaboratively solves it, producing an apparently random number that is unique for this group, but is also publicly verifiable, unpredictable, and deterministic. And this basically is your cryptographic proof of group consensus for the provenance mark, an unbreakable chain of documents. So thus it becomes a combination lock where the group collectively knows the combination, but no individual does in order to move additions forward. This is a lot more sophisticated, and I share this slide with you. I'm not going to walk you through it, but it is using VRFs and Sean Pedersen proofs and ratchet states, et cetera, to do all of this. So before we can do Frost provenance marks, we're basically using Frost beyond what it's been already proven for. So we're going to need help to do that. That being said, at least this does work in its naive case. So we can basically implement it and show that it is functional, vis-a-vis missing, vis-a-vis the naive use case. And then, of course, I would love for you to get involved with Gordian Clubs. In particular, what are the use cases that you're interested in for this technology? But in particular, where there are practical problems that true autonomous data objects could solve today, maybe in combination with other things. For instance, it could be that some OCAP technology that Agorix and other people are working on. Maybe some sub part of it could be solved, some problem with it could be solved with an autonomous data object. Obviously, as I just mentioned, we have these novel constructions that need cryptographic proofs. At this point, we do not have peer review of the club's protocol and code. Obviously, we're looking for companies that are interested in partnering on this tech, and we always need financial support, a variety of things, including the, what's been going on with what's been going on with government funding of projects has reduced everybody in the decentralized identities community ability to fund these types of things. So we're really needing support. And that support is not necessarily just individual support of companies, but just the social proof that, you are, offering us $10 a month on GitHub is something that we can use when we go to Human Rights Foundation and to other funders to basically say, hey, this is a technology that people are willing to commit to. So if you're interested in any of this, please email me or at team@blockchaincommons.com. And I think in summary, what we will allow some time for questions is, some dreams just need the right tools to become real. I think that Ryan and others will agree that sometimes it just takes time. Today we have these tools. Tomorrow, developers like you will use them to build systems to preserve human dignity. Are you ready to build uncapturable infrastructure? And I'm Christopher Allen, and I'm at Christopher A on almost all of the major social media sites. I'm going to stop sharing this now and give an opportunity for Q&A. Ryan, Gordon.
No questions for me right
Not so
now.
much a
Thanks for the
question.
demo.
Okay.
I'm going to have to watch the demo a little with more attention to step through and make sure I understand all the steps. But the thoughts that keep coming back to me going through this is how to communicate it to other people via analogies to other things, especially the way that the clubs advance being related to Git versioning. Especially the way that the club's state is a lot like a proof of stake blockchain. And possibly also, clearly it's at the state where, the command line tools are the key, but starting to imagine how this would look, even if the interface isn't built, like what would the objects look like to somebody who is doing this in a different look, could be helpful in reifying it in many people's minds. So those are just my thoughts from what I saw today.
One way of approaching that is one of the earliest things we worked on is how to deal with cryptographic seeds. And so we have like for example, our iOS app, Gordian Seed Tool, which you can get on the App Store, is basically an example of how to use that part of our stack, seeds, to generate keys to represent, to recognize seeds and keys derived from them and things like that, using our life hash and other techniques. And so on. So that's basically kind of a very, UX driven form of that. And yeah, so we're basically working not just at the command line level, but we're also the UX level, resources and time permitting.
And I'm definitely going to check that out and look at some of the other videos to make sure I'm caught up. So thanks.
Yeah, we have a whole playlist on Gordian envelope for instance, which I think is definitely essential. Watching to have grok what we're doing here, yeah, and also please reach out to me personally. I'm happy to set up a Calendly link and set up some time to talk to anybody who wants to ask more detailed questions about our stack or dive into particular details that maybe aren't covered by our videos. So feel free to reach out to me directly, wolf@wolfmcnally.com.
Thanks.
Ryan?
One thing that comes to mind is that since you're serverless, this might be a great application for CRDT's conflict free data types.
In fact, I've thought for a long time about how I would do CRDTs using Gordian envelopes. There, I think would be a great carrier for that kind of thing. It's not something we've done much experimentation with at this point, but that I would definitely welcome that opportunity.
We've done a little bit of experimentation with it over here, and I'm super excited about it. Maybe we could collaborate on that.
That sounds
Would be
very
great.
interesting. Yeah.
Cool.
Yeah, I mean, I think that's why I have the call out for use cases. We have some sponsorship in the past from the Human Rights Foundation, which protects journalists and activists of various kinds. Provenance marks are, in particular, are apparently random numbers. Um, there are other aspects of understanding the threats that we'd like to understand to address specific problems that, say, a journalist or an activist in an adversarial environment needs to be able to do. That would be an interesting use case. A lot of the inspiration for this is I want to enable the Amira engagement model. So back at the second rebooting at the United Nations, there was a Yoram use case for refugees that inspired in the third rebooting something called the Amira engagement model, which was an example of a developer trying to develop activism software without being vulnerable herself. A lot of what's in my mind is how do we protect software developers so that when they go through the Istanbul airport like that computer scientist did a few weeks ago, they don't get pulled aside and say, hey, you're potentially a bad actor, so we're gonna don't care about your free speech rights. We're gonna haul you off. That did happen a few weeks ago, and in the Istanbul airport. Fortunately, he was released, but that's the kind of stuff that's happening these days. So that's another use case. But I need to know more about the use cases. Okay, so last call. Anybody else? I don't see any hands raised. Thank you, everybody, for participating in the session today. We'll have a recording up later in the day and transcripts and other information. And then I'm working on a detailed article to talk about the history and where this all comes from. That'll probably be up later in the week or next week. But again, thank you for participating. Thanks.
Thank you, everybody.
Thanks.